Course 1, General. Damage mechanisms are common to a variety of industries, including refining and petrochemical. Pulp and paper and fossil utility are covered in this section. Mechanisms are divided into the following sections: mechanical and metallurgical failure, uniform and localized loss of thickness, high temperature corrosion, environment assisted cracking. Mechanical and metallurgical failure mechanisms. Graphitization. Description of graphitization. Description of damage. Graphitization is a change in the microstructure of certain carbon steels and half-moly steels after long-term operation in the 800F to 1100F or 427C to 593C range that may cause a loss in strength, ductility, or creep resistance. At elevated temperatures, the carbide phase in these steels are unstable and may decompose into graphite nodules. The decomposition is known as graphitization. Affected material. Some grades of carbon steel and half-moly steels. Critical factors. The most important factors that affect graphitization are the chemistry, stress, temperature, and time of exposure. In general, graphitization is not commonly observed. Some steels are much more susceptible to graphitization than others. But exactly what causes some steels to graphitize, while others are resistant, is not well understood. It was originally thought that silicone and aluminum content played a major role, but it has been shown that they have negligible influence on graphitization. Graphitization has been found in low alloy chrome moly steels up to 1% moly. The addition of about 0.07 chrome has been found to eliminate graphitization. Temperatures has an important effect on the rate of graphitization. Below 800F, the rate is extremely slow. The rate increases with increasing temperature. There are two general types of graphitization. First is the random graphitization, in which the graphite nodules are distributed randomly throughout the steel. While this type of graphitization may lower the room temperature tensile strength, it does not usually lower the creep resistance. The second and more damaging type of graphitization results in chains or local planes of concentrated graphite nodules. This form of graphitization can result in a significant reduction in the load-bearing capability while increasing the potential for brittle fracture along this plane. The two forms of this type of graphitization are well heat-affected zone graphitization and non-well graphitization. Well heat-affected zone graphitization is most frequently found in the heat-affected zone adjacent to the welds in a narrow band, corresponding to the low temperature edge of the heat-affected zone. In multi-pass welded butt joints, these zones overlap each other in covering the entire cross-section. Graphite nodules can form at the low temperature edge of these heat-affected zones, resulting in a band of weak graphite extending across the section. Because of its appearance, the graphite formation within the heat-affected zone is called eyebrow graphitization. Non-well graphitization is a form of localized graphitization that sometimes occurs along planes of localized yielding in steel. It also occurs in a chain-like matter in regions that have experienced significant plastic deformation as a result of cold working operations or bending. The extent and degree of graphitization is usually reported in a qualitative fashion: none, slight, moderate, or severe. Although it is difficult to predict the rate at which it forms, severe heat-affected zone graphitization can develop in as little as 5 years at surface temperatures above 1000 F, 538 C. Very slight graphitization would be expected to be found after 30 to 40 years at 850 F, 454 C. Time temperature transformation curves for heat-affected zone graphitization can be found in reference to affected units or equipment. Primarily hot wall piping and equipment in the FCC, Cadillac reforming, and coker units. Baetantic grades are less susceptible than coarse pearlitic grades. Few failures directly attribute to graphitization that have been reported in refining industry. However, graphitization has been found where failures resulting primarily from other causes. Several serious cases of graphitization have occurred in the reactors and piping of fluid catalytic cracking units, as well as with carbon steel furnace tubes and a thermal cracking unit, and the failure of seal welds at the bottom of tube sheets on a vertical waste heat boiler and a fluid catalytic cracker. A graphitization failure was reported in the long seam weld of a carbon half-moly catalytic reformer reactor interheater line, where concentrated eyebrow graphitization occurs along heat-affected zones. The creep rupture strength may be drastically lowered. Slight to moderate amounts of graphite along the heat-affected zones do not appear to significantly lower room or high-temperature properties. Graphitization seldomly occurs on boiling surface tubes, but did not occur in low alloy carbon half chrome moly tubes and headers during the 1940s. Economizer tubing, steam piping, and other equipment that operates in the range of temperatures of 850 to 1025 F, 441 Celsius to 552 Celsius, is more likely to suffer graphitization. Damage due to graphitization is not visible or readily apparent. It can only be observed by metallographic examination. Advanced stages of damage related to loss in creep strength may include micro-fissuring, microvoid formation, subsurface cracking, or surface-connected cracking. Prevent or mitigate. Graphitization can be prevented by using chromium-containing low-alloy steels for long-term operation above 800 F, 427 C. Inspection and monitoring. Evidence of graphitization is most effectively evaluated through removal of full thickness samples for examination using metallographic techniques. Damage may occur mid-wall so that field replicas may be inadequate. Advanced stages of damage related to loss in strength include surface breaking, cracks, or creep deformation that may be difficult to detect. Related mechanisms. Spherization and graphitization are competing mechanisms that occur at overlapping temperature ranges. Spheroidization tends to occur preferentially above 1025 F, while graphitization predominates below this temperature. Let's see. High magnification photomicrograph of metallurgical samples showing graphite nodules compared to normal microstructures shown in 4.2. Okay. High magnification of photomicrograph of metallurgical samples showing typical ferrite perlite structure of carbon steel. Okay, there's a graphite nodules, normal carbon steel. Softening, spherization. Description of damage. Spherization is a change in the microstructure of steels after exposure to the 850 to 1400 F range, where the carbide phases in the carbon steels are unstable and may agglomerate from their normal plate-like form to a spherical form, or from small, finely dispersed carbides in low alloy steels like 1 half moly to large agglomerated carbides. Spherization may cause a loss in strength or creep resistance. Affected materials. All commonly used grades of carbon steel and low alloy steels, including chrome half moly, 1 half moly, 1.25 chrome half moly, 2.25 chrome 1 moly, 3 chrome 1 moly, 4 chrome half moly, and 9 chrome 1 moly steels. Critical factors. Metal chemistry, microstructure, exposure time, and temperature are critical factors. The rate of spherization depends on the temperature and initial microstructure. Spherization can occur in a few hours at 1300 F, but may take several years at 850 F. Annealed steels are more resistant to spherization than normalized steel. Coarse-grained steels are more resistant than fine-grained steels. Fine-grained silicone-killed steels are more resistant than aluminum-killed. Affected units or equipment. Spherization can occur in piping and equipment after exposure to temperatures above 800 F. The loss in strength may be as high as about 30%, but failure is not likely to occur except under very high applied stresses in areas of stress concentrations or in combination with other damage mechanisms. The loss in strength is usually accompanied by an increase in ductility, which allows for deformation at stress concentrations. Spherization affects hot wall piping and equipment in FCC, Cadillac reformer, and coker units. Fired heater units Fire heater tubes and boilers or process units may be affected by a loss in creep strength, but equipment in general is seldom renewed or repaired because of spherization. Appearance or morphology of damage. Spherization is not visible or readily apparent and can only be observed through metallography. The paralytic phase undergoes a time-dependent transformation from partial to complete spherization, figure 4.3 and 4.4. In the case of 5% to 9% chromoly alloys, spherization is a process of transforming the carbides from their original finely dispersed morphology to large amalgamated carbides. Spherization is difficult to prevent except by minimizing long-term exposure to elevated temperatures. Inspection and monitoring. Spherization can only be found through field metallography or removal of samples of metallographic observations. A reduction in tensile stress or hardness may indicate a spherized microstructure. Closely related to graphitization. Spherization and graphitization are competing mechanisms which are overlapping temperature ranges. At temperatures above 1025, graphitization may occur after spherization. Below 1025, graphitization occurs before the steel is fully spherized. High magnification photograph of medical showing typical fairlight structure of carbon steel. High magnification of photomicrographic of metallurgic graphic samples showing spherized carbides. Normal spherized carbides.